I guess we should start by asking if you have a question. Any question before we start? Any question about Excel we covered in the last class? If no, then we will start with our probability as we have scheduled. So probability. Okay. So so we get started by understanding what is probability. I guess many of you already have idea what probability is, but we will define things more formally. Okay, so in order to have a more solid foundation. By the way, can you hear me or can you see the slides? Good, thanks. So to define probability, we are doing the classical method, okay? There's many ways to define those kind of things, but we will start by talking about the classical random experiment, okay? And why you start from that? Because probability start related to gambling, right? And gambling is you repeat doing certain thing, right? And then you bet on some of the outcomes, right? There are many possible outcomes from the experiment, right? Many possible scenario. Then you try to bet on certain scenario. Then if something happen, as you bet, then you win. Otherwise, you don't, right? You lose the money. So, so that's why I start with random experiment. And besides gambling, generally you can generalize to say what something is going to occur, right? And we have no idea which one to come. So that's why we talk about probability. If we know, then it's no longer probabilistic, right? And it can, or it's potentially can repeat many times. If something that can't repeat itself, at least in theory, that's very hard to say probability, right? Say, what is probability having this universe? It's very hard, right? Or what is probability that the sun will die out in millions of years? Those kind of things there's not repeating. Those is very hard to estimate. But when things repeat a lot of time, like total con already die, then you can repeat a lot, then you can conclude anything from the repetition of the experiment. Okay. So the second idea we talk about is outcome. Okay. Outcome is defined as the possibility of a random experiment. Okay. And you toss a coin, then your two sides, right? Head is an outcome, tail is an outcome. If you roll a 6-faced die, right? And the number 1, 2, 3, 4, 5, up to 6 are the outcomes. Okay, so we learn two things: it's a random experiment and its possibility is outcome. Okay, there's two basic concepts. And then it's event. Okay, event is defined as a group of outcomes, right? Say, if you more terminology with a set of outcome, if you learn set theory. And say for rolling a die, even number, okay, is an event that groups outcome 2, 4, and 6, right? An odd number will be 1, 3, 5, okay? Or small number can be 1, 2, 3. Event of big number can be 4, 5, 6, okay? So that would be a collection of outcomes, okay? And next is the sample space, okay? Sample space. And sample space is that contains all possible outcomes that is possible coming from random experiment, okay? And in the classical case, you know every possible outcomes, right? And say rolling a die, right, is 1, 2, 3, 4, 5, 6, right? You list all of them, right? Or penalty cake, right? either you get in or not get in, right? So there's two possible outcomes. And in other scenario, it's not easy to list all of them. Okay, so there's a lot of a lot of possible outcome. It's not easy to list of them, right? It's what is sample space of a stock market tomorrow, right? I mean, the stock market index may be easy to list, but what are the possible event tomorrow is very difficult, right? But for our purpose, that everything is well-known in advance, right? We know the sample space, we know what are the outcomes, but we just don't know which outcome is going to come out. Okay, that's the randomness has come from. We know the sample space, but we don't really know what might be the outcomes that comes out. Okay, but we know what are all the possible outcomes. Okay, that is we are restricting to this constraint, but this is classical way. Of course, there are many ways, but this is one thing we focus on. Any question before we proceed? Then we will define what's probability. Any question? So, no? Okay. So now we define what we call the classical probability, okay? And that what we do is what we call the log run frequency, okay? That is, you repeat the random experiment many times, right? And it's the ratio, okay, that is number of outcome favorable events, okay? And that is, you calculate probability of, say, even number, right? And the number favorable to the event may be any outcome that end up with 2, 4, or 6, okay? And that would be the numerator, right? You can see the numerator, okay? And the denominator is the total number of random experiments conducted, right? So you repeat many times, then it's how many times you repeat, okay? It's a ratio, okay? And why would it make sense? Because worth studying is in the most of this kind of experiment, say if you toss a fair coin and roll a die, right? Then you see this kind of ratio is more or less stable, okay? It's not changing, okay? So that's why things not changing, we can study it, okay? You toss a coin, okay, million times, for example, right? If the coin is fair, okay, it's not biased against head or tail, okay? You expect 500,000 ahead, roughly 500,000 tails, okay? Then you take the ratio, right? Half of them is head, half to tail, then we will say probability is 1/2 for head, and same for tail, okay? And why this worth study is, as we repeat, if you repeat this 10 million times, then you expect half of them also head, around half of them also tail. So this is worth study, okay? Because when you are saying probability 1/2, right, head or tail, that means it's more like equally likely. If you ask the next toes, is it head or tail? Then you say equally likely, right? In this case, okay. So that's why it's worth study in this case. Okay. Any question about this definition? Any question? I mean, it's nothing new here, but I would like to make sure everyone would follow this idea. Questions? No. Okay. Then let's start with example that is easiest enough to understand. It's roll a die, okay? And thank you. One is an outcome, right? And a 6-face die, so you'll be 2, 3, 4, and 5. And 6 are also outcomes, okay? And remember, all of the outcomes together will be the sample space. So the sample space is 1 up to 6, 1, 2, 3, 4, 5, 6 set of all outcomes, okay? And you can call an event outcomes will include it 2, 4, and 6. You call odd outcome will be 1, 3, 5. You call large outcome can be 4, 5, and 6, okay? You can call small outcome as 1, 2, 3, okay? And this PR is defined as probability of even or odd or large, okay, will be number of this event, okay, because it's a fair random experiment, right? Each outcome is equally likely, right? Then you run an experiment, then you expect half of them are even, half of them are odd, or half of them are large, half of them are small, right? So, in this particular case, you can just count the number. Okay? It can be simplified as 3/6, or you can further simplify to 1/2. Okay, so that is the definition of rolling a die and the probability associated with that. Any question? Good. Then we go to the next slide. So very often we would write things in the Venn diagram. Okay. So the sample space is the outer, you can see the outer square, right? Gives you S. It contains, the sample space contain all the 6 outcome is 1, 2, 3, 4, 5, 6, right? And then you can see they are put in different area, right? You can see 3 different circle. The green circle O consists of 1, 3, and 5, right? The circle E, the even have 2, 4, and 6. The large have 5, 4, 5, 6, right? And you can see why the overlap, but we talk about overlapping idea later, but you can see they have to be in this way in order to make it consistent with the circles, right? You cannot put 4 here because 4 is not odd. So that that is a graphical representation of these outcomes. And turn out this Venn diagram usually is very helpful to visualize simple sample space. Okay, I hope you have seen this. Is this one okay? This graphic may be new to some of you, but maybe many of you have seen it before. But is there any question up to this point? Okay, so seems like fair enough. So now we are going into a little bit more difficult. We talk about rolling a die twice, okay? And so the outcome, if you roll twice, then the outcome will become more, right? Because the outcome will consist of the rolling of the first times and rolling the second time, right? And it's not going to represent by number. It's not going to be 1, 2, 3, 4, 5, 6. It's not sufficient to represent, okay? In this case, the easiest way to represent by pair of integers, okay, from 1 to 6, okay? And the first entry is the outcome of the first row, and the second entry is the outcome of the second row, okay? And in this case, do note that we say 1, 2 is different from 2, 1, in the sense that first is 1, second is 2, and the first is 2, second is 1 are different, okay? In some application, if you care about the sum or product of these 2 numbers, then it doesn't really make a difference. But in other cases, this order can be different, okay? So that you have to be very careful with different outcomes, okay? And sometimes don't care, sometimes do care, right? Say for example, the application, right? If you talk about the annual income, right? Income of the company, right? Then you talk about you make $1 million first year, first half of the year, and make $2 million second half of the year. Then probably it's not different from you reverse it, right? In terms of annual income, right? But when you talk about predicting a trend, okay, 1, 2 is clearly better than 2, 1, right? 1, 2 is saying the company is making more money in the second half. It's an increasing trend, right? And 2, 1 is kind of decreasing trend, is making less and less money, okay? So that means that you might worry about the decreasing trend, but maybe very happy about increasing trend. So that can be different. So depend application. what you count outcome or non-outcome depend on how you measure things, right? If you just measure the sum of the two outcomes, then probably you don't distinguish. And how you call one is an outcome, one is not, you combine things, it depends on your application, okay? But now with the data storage is so easy. Usually you would record as detailed as possible, okay? But of course, you don't want to find detail, right? So you would be collapsing not useful thing, right? And keep the most useful thing, okay? Here, in this case, we assume that this order would matter a lot. Then in that case, we will keep the outcome like the pair, okay? If you think that only the sum would matter, then you don't really record in this way, okay? So here the sample space we have is 1, 1, 1, 2 up to 6, 6, right? And you can easily see this is 6 times 6, right? It's a total number of outcome is 36. Okay, so it's a pretty large sample space. And we care, as we said, we care about only the sums, right? Say the sum of two dice is less than 4. Okay, in that case, it will only consist of 3 outcomes. Okay, either 1, 1, 1, 2, or 2, 1. Okay. When you have 2, 2 is already more than 4. So less than 4 doesn't include 4, so less than. If we are including 4 will be less than or equal to. So we'll be more careful about the language here. Less than or equal to can be very different. Okay. In this case, we have 3 outcomes. Okay. And we know that the die is fair. Then each of one of the 36 outcomes are equally likely. So that's why you can just take the ratio 3 to 36, which equal to 1 over 12. Okay, is that okay for this example? Just okay. So that's good. And thank you. So the next thing is what we call operation on the set, or operation on event, right? And this is it's like a inverted U, okay? It's called intersection, okay? This is a set, and it's like N, okay? It's N. So find a common element, okay? Like finding a common factor, highest common factor XCF. Later, we see example what it means very clearly. Union is look for all possible outcome in the both events, okay? This is looking a common, looking for all. It's not or, imply finding the lowest common multiple. I mean, you will be clear what is going on in the following example. We use the superscript C as a complement. So some book would use T, some book was prime. So I think in the textbook they use prime. Okay, it just say dog there. But I use C because I want it to be a little bit more explicit complement. So what it means is things are not in the event, but in the sample space. Like Lord is outside. But anyway, let's see the example. It's more clear what we mean by that. So it's we have sample space 1, 2, 3, 4, 5, 6. Okay, the event are even, odd, and large. Okay, 2, 4, 6, 1, 3, 5, and 4, 5, 6. Okay, so we have intersection. Okay, is an event. Okay, so we have intersect 2, 4, 6 and 4, 5, 6. Find a common element. Okay. Only 4 appear twice and 6 appear twice, okay? So that's why E intersect L will be, so because you see you have 2 times here and 2 times here, okay? So that's why we have 4 and 6 as the intercept, okay? And let's use a color, okay? So look at O and L, okay? What are the common element here? Only 5, okay? Only 5 appear in the both set. So that's why the intercept will be 5, okay? And as we said, sometimes they will say and, okay? This is same as and when you say and, okay? Sometimes you see and, sometimes intersect. So I just try to make sure that when you read other books, then you understand what we're doing. And union is same as or, okay, as we see. So sometimes you see the book will say or, okay? And a union, E union L, you pick up everything there without repeating because the notation repeating doesn't really matter. So you can pick up everything there will be 2, 4, 5, 6 because this is all possible appearance. You don't need to write 4 and 6 again because for a set, the repetition means nothing, okay? Same as O and L, just write everything there, right? So it's 1, 3, 4, 5, 6, okay? Only 2 is not in here, okay? So for complement, E, okay, would be the thing not in E, but in S, right? So you just kick out the E here, right? It's no 2, 4, and 6. That's why we have 1, 3, 5, okay? And similarly, let me clear the complement of L, okay, LC, just take out the or the L from the S, that's what we left here. Okay, is it clear how the intersect, union, and complement here? So just to make sure, any question before we proceed to the next slide. Yes, complement is defined by sample space. Yes. Sometimes complement can be, usually is defined as sample space, but complement can be also relative to other things. So you will be things not in that, but that will be more advanced. But for most of purpose, if you don't say anything, then we just relative to the sample space. For our purpose, it's always relative to sample space. For class purpose, and for elementary, usually this when people don't mention is not in there. Okay, is that okay? Okay, if there's no further question, then you go to the next slide. So let's see the graphically, what do you mean by intersect, right? So you can see 2, 4, 5, 6, okay? 1 is not here, right? And 3 is not here, right? And the intersect is n, so there's things in common, okay? Intersect is n, remember this is n. And the other one is or, so this is union. Union is including everything, is or, okay? And this complement, okay? The E is in 2, 4, 6, and complement, E complement will be the thing not in E, but in S. Okay, S is the sample space. So that is the graphically all this thing to present. Okay, I hope there's no problem. Okay, so now let me talk about some property of the events that is frequently mentioned and also very useful. So first is called mutually exclusive event, okay? It's something that cannot happen at the same time, okay? And for example, okay, I can be in Hong Kong Island and Kowloon Peninsula are mutually exclusive, okay? I can not be the both places at the same time, okay? Of course, quantum mechanics will say you can be somewhere, but in the macro sense, I can only be one place at one time, right? So means if one thing happen, the other cannot happen, okay? Say we have raining, right? And no raining is mutually exclusive. Either you rain or you don't rain, okay? But raining and sunshine are not mutually exclusive, right? Although sometimes you think raining and sunshine is can happen at the same time, but they do have some time they happen at the same time. Okay, or for rolling a die, okay, number 1 and number 2 are mutually exclusive. Either you have 1 or you have 2. No, other one is 2, but you have 1, you can have 2. You have 2, you can have 1. Okay, but it doesn't mean that either of them are happening. Okay, because you can roll a die, can have 3. Okay, or 4. It doesn't have to be the same 1 or 2. Okay, just saying that cannot be both true. That we mean by mutually exclusive, okay? One exclude the other. So that is what the English means. It's very intuitive. If you want to a technical definition, you will be saying the interset or the N is an empty set. This notation means that nothing, okay? Means it's nothing, okay? There's nothing in common between them, okay? So that is what I mean. Is that okay? Okay. And the next one is exhaustive. Exhaustive means that if A and B exhaust is an exhaustive event, means that either A or B would happen. Okay. Okay. So it has to be happening. Okay, because it's including the union is the sample space, right? The union means that they together become the sample space. Okay, then sample space, we know everything in the sample space must one of them happen. Okay, so then it must be there. So that means the union are exhaustive. Okay, and of course it can be unique events A, B, C are collective exhaustive. Then union of three of them is a sample space. Okay. So what is exhaustive event? Say you roll a die. Okay. Even numbers and odd numbers are exhaustive. Okay. And also if you're large and small and even, okay, even the may overlap, but three of them together also are exhaustive. Okay. Of course, we see another example later soon, but I hope that's okay. Exhaustive means one of the things will happen. Okay. And A and B can intersect, they can have intersection. Okay. So what if you can combine the first and second, right? We can have mutually exclusive exhaustive event. Okay. And sometimes you can see the textbook refer to partition. Okay. Why? It's very intuitive because they're saying that the sample space S, okay, is cut into part 1, part 2, part 3. So partition is a cut them into several parts, and these parts are unrelated, okay, and they are mutually exclusive, okay. Each part, there's no intersection between part 1 and part 2 and part 3, and sum of all parts is the sample space. So here people ask, what does that mean? It means that if I have, say, Pi is 1, say P1, okay, and Pj is P2, I not to j, then for everything is empty, okay? And here 1 intersect 3 is also empty set, and 2 and 3 is empty set. Is that clear? Because I can be, j can be 1 up to n, right? When you pick up some I, then you have to pick something not I, okay? Because you have to say I not to j because it's very clear that this intersect this, right, is equal to itself, right? So it cannot be empty. So have to say not equal to be exact, okay? And here the definition is the partition, okay? We will say they're mutually exclusive as what we said, right? In this free partition of the three partitions. The three of them, they do not intersection, okay? And union three of them is a sample space, okay? So it will become more clear in the next example, but I hope you get the idea. Okay? And this partition is very useful when you calculate probability because usually the sample space can be very complicated. You want to divide things into several cases, right? If some of you learn finance, they know if you try to do the option pricing, then probably you would say, because you're looking at the future, then you can say, what happened in the future, the price goes up, what happened if future price goes down, what happened, the price doesn't change. and the day after tomorrow, and go on. So you divide things into many cases and evaluate different cases part by part. That is usually that's why we want to do that. Is you divide them into small and do divide and conquer, right? Break down the problem into smaller problems. So this is usually why this partition is being used. But anyway, you don't need to worry about this moment. Just some terminology, okay? So this example here, we have even number 246, odd number 135, and P will be the prime number 235, and B will be, I don't know, should be the big number. I don't know. This is the B. This is the B. I don't know why I defined that as B. And here you can see these O and B are mutually exclusive. Okay. And the reason why is there's no common element, right? 135 and 46 are mutually exclusive. Okay. But do note that OB are not exhaustive. Okay. Because you combine O and B, there's a missing thing is 2, right? So that's why I have to combine O, P, and B together. You can see you combine together, okay? Yes, everything, right? Because the samples, let me write a little bit here. Because the sample space is 1, 2, 3, 4, 5, 6, right? So why 3 of them are collective exhaustive? Because 1 you can find it here, right? 2 you can find it here, okay? 3 you can find it here or here, right? 4 you can find it here, okay? 5 you can find it here or here, okay? 6 you can find here, okay? So everything can be found in one of those, okay? So then the union is the sample space, then yes, okay? And you can easily check E and O are mutually exclusive because there's no common element, okay? And they are collective exhaustive because you repeat the same idea, you can find every single element in S in either E or O, okay? So that's why they are mutually exclusive and exhaustive. Remember, E and O are the partitions of S if you use another terminology. Okay, any question up to now? Because there are quite a few okay, it's clear. Good. Good. Then we will start by talking about axioms of probability. Okay. So the reason why we do this because of this is a classical way people define things. An axiom is we make some assumption and then we derive everything from that. Okay. So this is the I think is invented by Russian Kolmogorov in 100 years ago, 1900. They make this they make this, but probability is way back from Bononi in 1600. Okay, so it takes 400 years, 300 years to develop this axiom. Okay, so but we of course study the simplified version of the axioms, not the exact one, but it will be fitting our purpose. Okay, so everything can be derived from that. Okay, even if you learn more probability, then it will be just more complicated of what we have learned today. But the basic idea is all here. Okay, so let's get started. Don't be scared by the word axiom, but just a bunch of the thing that we don't prove. We just accept it as a fact, and we start from there. So it's the same as all the standard math texts. Is just we make some assumptions and start from there. Okay, because we have to start from somewhere. So first is let's get started. Axiom 1. Okay, axiom 1 you think is rather trivial. Is saying that what's probability? Okay, probability. Okay, must be between 1 and 0, okay? That's nothing but saying that we are trying to limit our attention to the scale of 0 to 1, okay? This is scaling, okay? We can say from 0 to 100, okay? Or 0 to 10, or 0 to 1,000, so fine. But we just from 0 to 1 to fit our convention, right? Because it's a fraction, because we define probability of fraction, okay? Then everything example is 1 over 1, right? So it must be, we'd be doing 0 to 1, okay? So that's nothing but just rescaling. Everything is must be 0 to 1, okay? Cannot more than 1, cannot be negative, cannot be more than 1, okay? The worst case you have 0, the best case of 1, okay? So that's definition, okay? The second one is telling you that, okay, we know everything, okay? So that means that the probability sample space is 1, okay? So that is the definition, okay? And remember, this is different from the definition of normal frequency, okay? Here, we don't talk about anything normal frequency, but just to define thing in this way. So we have a set of event, right, the sample space, and we say probability everything would happen, okay, is 1, okay? Is that okay? The first one is must be 0 to 1, and everything happens 1. So that is the maximum we can have is 1, and 1 is achievable. So that is what it is. The third axiom, okay, is saying that, okay, if A, okay, is a group of outcomes that are mutually exclusive, remember the meaning of mutually exclusive, is saying that there's no intersection between every element, okay? This means these intersect them, they are empty. There's no common element between them, okay? And how to evaluate the probability of this event A? Probability event A with just the sum of the probability of each single event, okay? Okay, so that is the 3 axioms. And later you will see this one carry us very far, okay? Looks very trivial, right? But this is usually how the math goes, is we make the simplest assumption, we try to derive the more complicated thing from the basic, okay? So this is the idea of the probability. Okay, if you, some of you go to study math, then you will see the same thing. We build things from the very scratch. Any question before we proceed? Okay, is that okay? I mean, it looks very intuitive, but any question? Is it okay? Okay, just repeat again. Either is probability must be between 0 and 1, and probability of the whole sample space is 1. Okay, if an event is consists of outcomes that are mutually exclusive, then the probability of that event will be sum of the event that constitute it. Okay, the sum of them. Okay. Okay, I assume there's no problem because I saw there's no problem. But let's go into the next one. Okay. So, and let's see how we are going to work on this fair die after that rubric. Fair dies using the axioms, okay? We don't rely on the idea of a normal frequency, okay? There's no more normal frequency. Normal frequency is a definition of classical probability, okay? So you can repeat the experiment, and you can start to do things. Here we make some, we just start from scratch, okay? So with sample space, okay, we call 1 to 6, okay, number 1, 2, 3, 4, 5, 6, and we are saying the fair die, okay? So outcome is equally likely, okay? So the first thing equally likely means we have this. 6 of them have the same probability, okay? Is that clear for this part? Is that okay? I hope there's no problem. Now here comes the interesting part, okay? Okay. Remember, axiom 2 said what? Probability of S is 1, right? And S is consists of 1 up to 6, right? And these outcomes are mutually exclusive, right? So that means that probability 1 plus probability 2 and so forth, right? To probability 6, right? Should be equal to probability S, which is 1, okay? And they're all equal, right? So which means that we have 6 of the same thing equal to 1, right? So then it will be 1/6. Is that clear? Uh, is that okay? Good. So that is how you know why this 1/6. Okay, that's from definition. And if you cover probability E, okay, event E will be consist of 3, 4, 3 and 4 and 5, sorry, 2, 4 and 6, okay? And we already know each of them is 1/6, okay? So that's why even will be 1/4, sorry, 1/2. Okay? Is that clear? If there's no further question, we will have a break of 15 minutes. In the meantime, you can ask me a question. Break until 1:31. Okay, it's a break. So you can ask any question if you want. Some of you asked me, do we continue slide on Excel? I guess at the moment is we will talk about more later. But because we cover the already covered the mean, variance, and mode, so I guess it's not. We will not talk about that. But after a little bit about talk about, I think after a few class we talk about that. But the moment I guess the Excel is sufficient for the prep currently now, unless some of you want me to cover more currently, but I will defer until later stage. If you are hurry learning about that, because you can go to the data camp and check out, because I think that would contain most of things we needed for the purpose. But unless you want something particular, you let me know. I will try to see if there's sufficient interest. We will talk about it earlier. Otherwise, we will defer the programming later, because they will be more efficient in talking this way. What is intersecting? So someone asked me axiom 3. So let me share the screen again. Some of you asking me this about what is intersect is 0 is empty set, which means that they are mutually exclusive. Just that means this outcome has no common element. Okay, say here the application we have is 2, 4, and 6. They are outcome already, so that's why they're not event. So that's why they're not the same thing. O and J means 1, 2, or 1, 3. This IJ can be just any number between 1 and n. Is that clear? Query? Quan Yi? Yeah. Just feel free to ask. I'm around. Someone asked me why the adjustment factor is y is n minus 1, but not n minus 2 or n plus 1. Okay. So the reason, as we said, will be explained in chapter 6, that actually you can prove why n minus 1 is the better. But intuitively, why that's the case is you can imagine there's a sampling error. When you do sample, there's some mistake. So that's why we expand larger. So that's why you divide it in the smaller number that make the variance larger. So that's why it's not n plus 1 or n plus more. And why n minus 1 but not n minus 2 minus 3? It is somewhat more elaborated. We need some proof for that. But turn out to be n minus 1 is the best. We'll define what to mean by best, but that would be in general that we call the unbiased estimator. So that's why if you do that on average, using this will be more accurate than using other. It's n minus 2, you'll be inflate too much. N minus 1 is the best one. And why is the best, we don't explain now, but it will be covered in when we talk about estimation. Is that okay? I mean, Henry. I'm sorry I have to keep you in dark, but if you're curious, you can just check the slide over there, which uploaded in the Blackboard. So you will see the sample variance turn out to be the expectation of that will be what we want to do. But at the current moment, I cannot prove it because we have to wait until then. But I hope that will be clear. And you will say why not n minus 2 actually turn out to be sometimes the n minus 2 will be good in certain we do regression, but for the general case we do is n minus 1. Okay, but so I hope that would be that's why when you do the Excel, they will have the variance P, variance S, standard deviation P, standard deviation S. So that is something that we would be always doing n minus 1. I hope that will be clear. But this is a good question. So 3 more minutes, then we will resume the class. And Henry, just to saying this is only important when the n is small. So you can see if the n is more than thousands, then you actually don't see a difference. So when you do with large sample, then you don't really worry about this part. And that would not be a big issue. But when you have sample like less than 300 or just a little bit, then it will be important. Say when you do medical experiment and then you just do less than 100, then it will be a big issue. But otherwise, when you do economics, usually you do way more than 100. I mean, usually thousands sometime, very often, unless you're talking about macro, but the microeconomics, usually you do more. So it's not a big issue, usually. But anyway, just take the n minus 1, then that'll be fine. Okay, 2 more minutes. Let's see if you have any more questions. One minute. Okay, I guess we should resume our class. Okay. So, oh, there's some question. Good. Oh no, the data camp is just I assign it for you to have. You want to? I just assign the relevant thing because there's too many things in the data camp. So it's not the assignment. The assignment will be something that I assign on the blackboard. I will assign the assignment will be put it later. The data camp is just for you to work on yourself if you want to have you learn more. It's not part of the assessment. If I put that in the assessment, you will see, but currently no. Yeah, it's optional. Unless no, yeah, it's optional task at the moment. There's nothing that, I mean, the thing I just assigned there is just for you to work on. It's not something that you need to be concerned at the moment. Unless I explicitly put in the homework. So the homework will be put on the blackboard later. I think after the airdrop period, I put that on maybe next week. I put on the first homework. Is that okay? Is that clear? Check them. Good. Let's revise because of the break. So just let's go back. We no longer talk about the long-run frequency. That would be the starting motivation for having probability, but that is not necessary for definition. So we will start from the assumption we make on the probability is always axiom 1 is between 0 and 1. The sample space is 1. If outcomes are mutually exclusive, and that the event come up with n mutually exclusive outcome, then the probability of that event will be sum of the probability of each outcome. Okay. And now we know if we say a sample space of a Ronge die, if each outcome equally likely, then we can define things very clean. Okay. So let's have one rule that we will be often used that would be based on axiom 2 and 3. So by axiom 2 and axiom 3, axiom 2 is saying, just to repeat here, right? Axiom 2 is saying that the probability of sample space is 1, right? And axiom 3, axiom 3 is if this a event, right, will be the sum of or outcome if the outcome are mutually exclusive, right? Just to make sure that you remember that. Okay. Now, one special case of this A and O is a partition. Okay, it's A can be considered the event S. Okay, O can be some event A and its complement. Okay, S can be written as A and AC, A complement, right? Because they're mutually exclusive. Okay, and that means, right, combine these two will be probability S, which is 1, will be equal to probability A plus probability A complement. Okay? So you can rewrite this and you have this formula. Why this formula is important is because when you want to calculate event A, it can be very complicated, okay? But its complement, okay, which is AC, can be easily found. So that is a shortcut to do a lot of calculations, okay? Is that okay for this one? Okay, the how we derive that. Is that clear? Okay, no problem. Okay, so let's see the example. You will see why we want to do that. Okay, so suppose the roll die twice. Okay, we remember this example. We have 36 outcomes, right? 36 outcomes. Okay. Okay, and what are some of the face value less than 12? That's a lot, right? You can easily see the lot, right? Say 1, 1, 1, 2, 2, 1, 1, 3, 3, 4, and a lot of things. Right? You can see a lot of them. Okay. Then you can figure out, okay, can I find the complement? Is it more easy? Okay. Less than 12, right? You know less than 12, actually it's very simple because lot less than 12 is only one case. It's just 12, right? Coming from 6, 6. Okay, only one case. Okay, that means I want to calculate this, right? Will be what I want is only one case, right? So it's 1 over 36. Okay, then with the answer, right? Because instead of calculating less than 12, I calculate no less than 12. And no less than 12 is only one single event, right? Which is one single outcome, or it's just 6, 6, right? Then it's just 1 over 36. And why 1 over 36? Because each outcome is equally likely, right? If you can have a table, right? It's 1, this is up to 6 here, and 1 up to 6 here, right? And this may be the first, this is second, right? And turn out to be the 36 of them, right? You really want to, the question is asking you to calculate this guy, right? Then you really, yeah, it depends. Somebody asked me whether I have A or AC, doesn't really matter, depending on how you define A. If you define A as the something A, then this is, I mean, if you don't like this one, you can change to this one. Depends on how you define A here. I didn't define A, but doesn't really matter. If you define A is less than 12, okay? I mean, I'd be lazy, okay? The row is less than 12, then you write in this way or the other way around. Is it young sub? Is it okay? Yunsu, is it okay? Depends on how you define A. But I mean, if you like, you can define this way. Maybe this is more natural. But I hope you see what I mean. Is that okay? At this point, maybe I should change it. If you feel it's confusing, I should write that down. I should change a little bit. If you think A and AC is, maybe I should write what's A. Okay. Is that okay? Well, of course, it's a must for us to write the formula when do calculation. I think you would try to define carefully and apply for you to understand and make clear. Of course, put it this way, if your calculation is correct, then probably no one would care. But if you just write down the answer, if you do it wrong, then there's no partial credit, right? So if you done things, you are very smart, you just can see the answer, you're genius, then probably it's not a big issue. But in the case you make a mistake, then probably you would better to write some steps, right? And for the exam, usually if I don't ask you to write the steps, then you don't need to. But otherwise, if I said so all the steps, then you need to write the step. But otherwise, I would just care about your final answers. Is it okay? Okay, so I think same all the assignment and the thing is like if you make correct, then probably it's okay to skip some step, but the risk of you. Well, usually I should define what A is, but I just I make the slide. I should define what the A is. I should do it, but I think I was being a little bit lazy, but it should be. Otherwise, people don't know what you're writing, as you can see in this slide here. I mean, in general, you should define things when you really want to. Well, of course, usually you don't need to write this, right? You don't want to write. Suppose the sum let say, suppose if you want to be something like, let X be the sum, okay? And we'll say probability that X is less than 12, right? Will be equal to 1 minus probability X is bigger than 12, right? And then you can write 1. Actually, this is the same as equal to 12 because there's nothing more than that, then it's 1 minus. Okay, you can, if you want to be a little bit less trick, you don't have to write A because you can write in this way. I mean, it doesn't really matter as long as you make it clear. Okay, so it's not something you have to do in a certain way. It's not a prime. We are in the college, right? It's not something that you need to do things in one way or the other, but you just make it clear. People can understand. And if you are misunderstood or you make a mistake, I can still give you partial credit. That is the purpose. Is that clear? This is general principle. I guess it's same for all other class too. I don't know other teacher, but I think this is something we should apply to our college education. But anyway, before we proceed, any questions? Good. If no more, then we go into the next slide. Okay, I clean the screen. So we have, we call it addition rule. So this is something, again, is a very useful rule. If the probability of the n actually is an intercept, right? So this what is n will be, is a color, and here is intercept here, okay? Will be sum of the probability of the two net of the union or, okay? It's always here. So basically it's A plus B minus or, okay? And actually you can see that from the Venn diagram, right? So if you look at the area like this is suppose this is A, okay? And the blue one, say, the blue one is B, right? So it should be the A area plus the B area minus overlap, right? Because you double count, so that's why you would be so you will be A and B, you take out the whole thing. So put it this way. So maybe the green one here. Okay. So the intercept is the green thing, right? Okay. And it will be the circle A and the B. Okay. And you want to take out this. Okay. Then what you left is this guy. Okay. This one may be a little bit not easy to see, but you see the other way around. Is you just move this to the other side. So this guy, okay, plus this guy, okay, should be, you take the circle, okay, and the other circle, okay, and you take away the overlap, okay. So that would be how you relate the intercept and the union. Okay, this is a very useful technique. Okay, and this can also be proved. Okay, using the axioms, but I'm not going to show you, but it can be done by axiom. Is that okay? Let's see the example. Maybe that would be easier to follow. So now I have an example. I roll a die once, okay? Maybe a die once, okay? And I'm asking, oh, sorry, that's double off. That's one off, it's fine. Probably of an even number, and number greater than 3. Okay. So even number is what? Is 2, 4, 6. Okay. And number greater than 3 is 3, 4, and 5. So 4, 5, and 6. So this usually while you write this in this way. I mean, usually you write this. So you define what A and B is. Okay. And then A and B, A intercept B, right, will be number greater than 3. Okay. The common element, right, would be 4 and 6. So that's it, right? So it's just 4 and 6, they are common. Okay. And then probably A, right, because it's fair, so it's 3 over 6. B, again, 3 over 6, right? The intercept would be 2 over 6 because 2 elements there, right? Each element is equally likely. And what is the probability that OR would happen? Okay. Applying the formula will be A will be this plus this minus this, right? So it's 3, 6, 3, 6 minus 2, 6. Okay. 3 plus 3 is 6. 6 minus 2 is 4. Okay. And you cancel out, right? Then it's 2/3. Okay. And alternatively, you can do the following, right? The union A and B, you just pick up everything in A and B. So it's 2, 4, 5, 6. So let's say 4 elements here. So 4 out of 6, again, is 2/3. Okay, so you can see the same here. And why you want to do this is, again, same as the example, it's a complement, because sometimes it's easier to calculate or sometimes it's equal to n. And this is the way you make your calculation simplify. Is there any question? I guess it's a little bit increasing, little bit more complicated. But if you're okay, then you are with me, then please type okay, so that I know you are around, or at least you're following. But if you have any question, then please let me know. Okay, I see everyone's okay. At least no one say not okay, but if not okay, then let me know. I can repeat a little bit. Okay, very happily that everyone is no problem. Then we are going to this one. I hope this is now is not something difficult to see. Actually, we have that when talk about the, if A up to N are partition sample space, remember what they mean is the sample space, okay, is cut into A1, A2, blah, 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 up to AN, all right? And they are mutually exclusive and everything exhaustive, okay? You say, it's like a cutting a cake, okay, into different pieces. And some of them is 1, okay? So that is, you divide them into different cases and you analyze, okay? So that is the rule. And how this rule can be useful, let's see the example next page. Okay. Let's see the following. Okay. Now I roll a die twice. Okay. What's the probability that having the sum is less than 11? Okay. And here we care about the sum. So that's why the sample space we care. We don't need to make our life difficult. We don't need to say one, I say outcome, 1, 2 is an outcome, right? You can just care about the sum. So we can just say the event, right, is AR is the sum of 2 results, okay? But do note that when we write in this way, it is not going to be equally likely, okay? So A1 and A2 is not going to be having same probability, okay? So that is, have to be careful about this, okay? It's no longer the same thing, okay? Now, you know the outcome of the sum, you only have 2 to 12, right? The minimum is 2, the maximum is 12. Minimum 2 come from 1 and 1. 12 is come from 6 and 6. Okay, so the minimum is 2, the maximum is 6. So it's 12. And What now we want is to see the probability, okay? And it's a fair die. We know A12 is going to be 36, right? Because it's coming from 12, it's only come from 6, 6, okay? And 11 is only coming from 5 and 6, or 6 and 5, right? And these two are mutually exclusive, right? So each one is 1 over 36, okay? So you can just add them up. We don't need to minus, right? Because they're mutually exclusive, right? So just add up each side. If they are not, then you have to subtract their intercept, okay? But anyway, you don't need to worry about that part. Okay, so that's why it's 2 over 36. Is that clear? Now we want to say less than 11, right? So it's very difficult to find because you find 2 up to 10, right? Of course, you can do that, but it will be easier to find the complement, right? So we just like 1 minus 11 and 12, right? And 11 and 12 is add together is 3 over 36, right? And it's 33 over 36, right? And you end up in 11 over 12 when you divide both numerator and denominator by 3. Is that clear for this one? Any question? Any question? No, that's good. That's good. It seems like everyone you are following. Now I clear the screen. So now I'll go to the next one. So now we talk about some gambling. Okay. So because that is something you also see that in Macau or in other place in the world. So it's odd ratio. So it's odd. So people talk about odd. This odd ratio is closely related to odd you learn in the you see in the casino. I do know that I don't encourage gambling or what, but just historically this probability related gambling or horse racing or those kind of things related. But anyway, so what do you mean by odd ratio? Okay, odd ratio, there are two careful definitions in favor of or against, okay? But you see later, you see very similar, okay? I'll just reverse each other. So odd ratio in favor of event A will be the probability A over its complement, okay? To simplify, will be probability A over 1 minus probability A, okay? Other hand, if you against it, will be inverse, okay? Just reverse the numerator denominator. So this is what you have. Okay, so there's nothing to understand, but just definition, okay? It's definition. So this is, whether you know it or not, there's nothing to understand because it's just defined, okay? Just define. And then of course, this definition must have some use, right? Otherwise, why we care about this definition? Because there's nothing interesting unless there's some meaning. So let's see whether it has some meaningful application. Is that okay for definition? Okay, I hope it's clear. So let's see the next page, okay? And the odd ratio, okay? And you will see in the casino, you will see they call the betting, you say odd of 1 to 4, okay? And usually it means that if you making $1 bet, okay? If you win, you get $4, okay? Of course, if you lose, you get 0, okay? So 1 to 4 means you get 1 and then you bet 1, okay? You get $4, okay? So what is a fair bet, okay? Fair bet means if you try to bet on this on average, you are not going to make any profit or loss, okay? And if you make $1 bet, you win $4, which means that you are winning only if you're winning 1/4 of time, you're losing 3/4 of time, okay? Means you win $1, okay? You lose, you win $4, of course. You lose $1, okay? only you get win means you get the dollar. So only in this, okay, you will be sorry. Sorry, it should be. Okay, it should be something like this. It's the odd ratio, okay? The odd ratio of winning, okay? So odd for winning, okay? In this case is probability of win, okay? Minus probability of lose, right? So in this case is we win with 1/5, okay? We lost with 1/4/5, so it's the odd is 1 to 4, okay? And this odd 1 to 4 is inverse of the betting odd, okay? In that case, we will see this is in general, that is not making any gain, okay? You can see here why on average you are making a breaking even, right? Because 5 out of 5 times you win $4, and in out of 40% of time you win. So 80% of time you lose $1. Okay, on average, actually, it's a break even, right? I think it's clear. Is it clear why this break even? I mean, 1/15 of time you are okay. Put it this way: suppose you are having a 5 bet, okay, and you are winning $4, okay, and out of the other 3 cases minus $1, minus $1, minus $1, minus $1, they break even. This assumption, we assume this is the case. Okay, if this is the case, then this is called fair bet, right? It's a fair bet because you don't really care you become a casino or you become a gambler. 5 a.m. is it okay for this one? Okay, and but this only fair because you have this probability. Okay, and if you calculate the odd in favor of winning, okay, that is equal to 1/4. Okay, and this 1/4, okay, you reverse it, should be the odd. Okay, should be this one. It's related to this one. Okay, so this is related to this one in the following manner. Okay, or odd ratio against the outcome. Okay, so basically, if you see the odd of in the casino, you see the odd of 4 to 1. Okay, actually, you can imagine that people or the casino or all the people believe only 25%. No, it's the odd ratio is okay. Odd ratio in when you talk about random experiment, okay, the odd ratio is a fixed thing, right? So I give you odd ratio of roll a die. The odd ratio in favor of 1, right? Say if you roll a die, odd ratio for 1, right, will be the probability of 1 and probability 1 complement, right? So it's 1/6 over 5 over the 6, right? It's 1 to 5. For this kind of experiment, that's fixed, okay? But in casino, right, you should try to bet soccer or bet some horse racing, then the odd ratio sometimes will change, right? Depends on how many people are betting, they will change. But by looking at this odd ratio, actually you can see how the casino or how the people, how the market think about one of way or the other. Is that clear? What is that? Is that clear? 9. Okay. If you give me probability, then the odd ratio is fixed. Okay. But in the real world, sometimes the probability is coming from how people view the things. Just like the horse racing, right? If you notice, the odd ratio, how much you can make by winning, keep changing. Okay, of course, when you bet, the value is fixed, but after you bet, the value keep changing. Okay, is that clear? So that is when you see the odd, then you can try to guess what's going on. Okay, so if you try to, I think in Taiwan they have somewhat try to bet everything in the future, or same in the UK. I think UK have a lot of things you can bet on everything. Every single big thing happening in the real world, they can bet. So maybe you can, I think UK they can bet on who will win the next election in the US, whether the Trump win or the Biden win. They can bet on those, or when the fire in California will go out, or those kind of thing, or those things, everything can bet, and then you can see the probability based on that. Can be inferred from that. If you think the casino is large enough, then it's more like less fair. You can infer the probability from there. Against, you just reverse it. You can see the against because it's the ratio. The odd against the winning is exactly the odd ratio you see. Kakai, is it clear? Because you reverse this is exactly 4-1. Okay. Okay, any more questions? Why we need to reverse? Well, it depends on whether odd for or odd against. So it doesn't, I mean, but I don't know the casino, they always use it this way, 4-1. You ask why not 1-4, but this is how things being done. I don't know why, but that is what the terminology is. Is that okay? I hope that solved some of the answers you have. So that's why in English sometimes they say what's odd of having this. Actually, they're talking about probability anyway. But okay, so if there's no problem, we go to the next slide. Any more questions before we proceed? It's a little bit trickier, but I don't think it would be problematic just with the clear about definition. There's nothing new here, but just some definition and some application of the odd. Okay. So here an example, Rohit Fredai wants what is the ratio in favor of 6, okay? And in favor then is 1/6 over 1 minus 6, 1/6, then is 1/5, okay? Then you reverse it or the against it, then it's 5/1, okay? So that's why you reverse, okay? If you calculate it for favor, but of course you can do the against, exactly the bet. So it means that you will think it's a fair bet, okay? If you say 6, I give you $5. If you lose, you get 0. Then it's a fair bet. Okay, we don't really mind you be a casino or you're the gambler. Okay, so that is the idea. Is that clear? Is that okay? Any question? If okay, then please type okay, so that I know you're with me. Thank you. So now we are going to a little bit more trickier thing, if that's okay. So talk about the conditional probability. Okay. That is a very important concept is because very often we learn more about the new world, then the probability had to be updated, right? One common example in military, right, is saying that, so this is the area, sample space, right? This is the area we are interested in, right? And we know, say, suppose we want to strike a person or enemy or a tank or a weapon, right, who has been moving in this area, A, right? So this is somebody want to hit, okay? And you know, using the color blue, the general come back say, oh, we send a missile we hit this area B, okay, some point in B, okay, then probably we say, oh, then as a commander, you want to know, okay, we know we hit B, how likely we have hit the target A, okay? We want to, A is moving around in the area green, and then our thing we hit some in the B, okay? Or maybe we just completely hit the B, maybe a nuclear weapon, hit everything in the B, we destroy it in B, okay? So how likely that we hit that object, right? That is something common, right? And if you learn the news, usually these days, we talk about A maybe the aircraft carrier by US, and B maybe the anti ship missile, right? Same idea here. Okay, but anyway, or something we also want to update is we learn about information from the business we want to update. Okay, so that is something we want to know. Okay, and now the tricky part is because of we know, say, B is going to happen. Okay, B has happened. Okay, the sample space will shrink. It's no longer S, right? Should be shrink to from S to B. Okay, then when you learn, remember what you learn is from axiom 2, the probability B, okay, you know B had happened, that should be 1, right? Because you know B is the new sample space, okay? And we know everything is between 0 to 1, okay? You should rescale everything, okay? Then the probability A, right? You should be, if you really care about the graph, right? You'll be something like this, right? Should be the area of this over the area of that, right? So that is, you remember how we hit it, right? The probability you hit everything here, you destroy everything here, right? What's the probability of hitting the target A, right? Will be the area of this over the area of this blue circle, right? So, but in the other words, right? Basically, you are rescaling everything, right? You shrink. So that's why the definition of conditional probability A given B, okay, will be, because everything will be 1 by having probability B, okay? So the denominator will probably be, okay? Because probability B is 1. So that's why everything will rescale, okay? And the numerator, why is A and B? Because you know B has happened, okay? Anything outside B is impossible, okay? So we have to be only thing in the A and B, okay? Is that clear for the definition? Is that clear why with this definition? Okay, just to repeat a little bit once more, because we know B has happened, so B must be, everything must be rescaled to 1, so it must be this case. And we know A happened, then only we care about intercept, right? Because B has happened, so it must be intercept B. So that is the idea. So basically this one, because B has shown, must be this one, and we rescale. Yes, exactly, Yongjun. So that's why it must be divided in this way. Yes. So because the relevant thing is B, right? B has happened. So it must be, the first thing must be only this thing is relevant, right? Because A, let me erase it, right? Because A is 2 part, right? A has 2 part. A has either A intercept B complement and A intercept B, right? We know B has happened. So this thing is no longer true, okay? And that's why you left this guy. And because we have to rescale everything into 1, so that's why we have this one. So this is intuitively this formula, why it makes sense. Of course, you can prove it, but we don't do it here. But that is intuitively what it means, and also makes sense. Of course, if you don't like the intuition, just this is definition. Just remember it, this definition. And for your purpose, remembering is not bad. Later, and you will know why this is true. But is it okay? At least if you don't understand, at least you can memorize, you understand the ratio, it's a ratio. Okay? So let's do the example, okay? Now I roll a die once, okay? And the sample space is 1 to 6, and E is the even number, L is last number, and the intercept is 4 and 6, so it's clear because only the common element is 4 and 6, okay? Now we are saying outcome is large, so someone tells is large, so L is true, okay? We know it's large. What's likely is event E, okay? So the new sample space is L, okay? So actually it's no longer, E is actually relevant is 4 and 6, okay? So if you, to be technical, you want to say E intercept L, right? Actually the same as this guy should be, because you know the only relevant thing, okay? This is how you come from here, okay? This is, you know this happening, okay? So L have the new sample space, we only have 3 numbers, okay? And out of 2, right? So it's each number is equally likely, so it's 2 over 3, 2/3, okay? This is how you can derive from the principle, right? But turn out to be, you can be more smart using the formula, okay? The definition, probability, E given L will be a fraction. The numerator will be probability of L. The numerator will be their intersection, okay? So is L will be given by 3 over 6, okay? Because 3 element out of 6. And intercept L will be 2 element here, 2 out of 6. It'll be 2/3, okay? So turn out to be the same thing, okay? So that is make your life easier. You don't need to do it in this way because this is a shortcut. Is that clear? Is that okay? So just definition, but if you don't care about the intuition, this is just definition. Turn out it works, and you can have it, memorize it, and if you do enough exercise, you know it. So it's not something. Don't worry about. You don't memorize because enough exercise you know. Okay, and this is a very common thing. So don't worry about that. If no more question, then we talk about this a little bit before we end. So I want to talk about this multiplication rule. Okay, this nothing new. Okay, this is rather simple. So let's go back to the previous slide. This definition. So what you're going to do is this and this. You can multiply both sides by probably B, right? So cancel out. Okay, that means that the intercept, okay, can be written as probability B times probability A given B. Okay, so that is what the formula on this slide is. Okay, so that's why you have you can write in this way. Okay, and A and B can be just arbitrarily defined, right? So that means we can flip A and B and A. It doesn't really make a difference. Okay, so the two things happen together. You can conditional on one thing and multiply how likely it is. And in statistics, this is called conditioning. Okay, and this is very useful technique when you do the probability, right? When you want to say how likely the join it together, then usually we would divide into in this way. It's a little bit abstract here, but later when you face some problem, you will see this is very convenient property. Okay, so let me end this slide with example. Okay, so now we have a little bit overrun at 1 minute, I guess. So we have earned with 3 black ball and 3 white ball. So it would be a ball with 3 black, okay, and 3 white. Okay. So what we are going to do is we will be asking a hand. Okay. He's going to pick up 2 balls. Okay. And the first ball is called A, second ball B, doesn't really matter. And without replacement. So we pick it up and to pick it again. Okay, we don't put it back. So that's why without replacement. Okay. Then what is probably that the both balls are black. Okay. So the A will be the first ball is black. The second ball is black. So there's something we want to check. Okay. And of course, there are 3 and 3 balls and 6 balls. So you can count every scenario. Okay. But we can do it easily by looking at the definition. So probably A, the first ball is black. So out of 6 balls, you pick 1 ball is black, then probably is 1/2, right? Because 3/6. Okay. And probability of if you pick up 1 black ball, so what you have is indeed is not this, right? Is you pick the black ball, so what you have is this guy. Okay. It's gone. So what you have is, what probability you have black ball is 2/5, right? Because the black is gone. Is that clear, this one? Okay. So the intercept will be the multiplication of 2, right? Is probability that you draw a black, okay? See, okay? And then after first black, the second black again, okay? So that's why it's the multiplication of 2 is 1/5. Okay. Any question? I guess we end here because I think overrun a little bit. Okay. If no, then have a nice weekend. Thank you very much. No, we will only have quiz after we finish everything. So I guess not. Even the next class we finish, then probably we will defer to the maybe next Thursday because we will finish next Tuesday. I think we will do the next Thursday. I think we'll quiz next Thursday, but no quiz next class because we finish it and then we after the 1 class with the quiz. So don't worry. Enjoy the weekend. I stay around to answer any question you may have. Thank you and bye bye. So let me know if any question. I am happy to answer it. So some of you asked me the 25, page 25. So let me clean this slide. So go back to 25, and people ask me to use Chinese. So Peter, you want what do you mean Chinese? Is Cantonese or Mandarin? Both okay. Okay. Sorry, I have to use Cantonese or Mandarin here because someone asked me especially. 咁你嗰個問題話 odd ratio 係1:5定5:1？係 odd 就係通常係5-1嘅個 odd 就係 odd ratio 就會寫中比例咯。咁呢個 odd 就你見到呢個題目都係咁樣4:1或者叫做4-1咯。得唔得啊 ，Peter？哦，即係 odd 嘅意思，呢個 odd 嘅意思即係話喺呢個5:1嘅話，你俾1蚊就贏就贏5蚊，輸就冇咗1蚊咯。咁就係叫5-1或者5/1，咁就 odd 咯。咁 odd ratio 咁呢個同 probability 冇關係嘅。咁但 odd ratio 嘅話咧就係話由呢個機會率佢計出嚟嘅。4/1咯。1/5啦，呢個呢度係啦，呢度係啦，呢個1/5咁，買1/5咯。 咁但係1:5嘅意思其實就係話佢哋個 odd ratio 嘅比例，如果佢係 fair 嘅話，就係1:5咯，得唔得啊 Peter？odd 嘅中文我真係我要查一查，odd 就係點樣先係 fair？即係話如果我叫你呢個1:5 ，OK， 1:5贏嘅機會咧就係1/6，輸嘅機會5%。咁你無論你做賭場又好，做賭仔都一樣噶嘛。即係你想做邊邊都冇所謂嘅，咁就係 fair。即係你唔介意做邊邊都一樣。odd 嘅中文啊，我查一查有冇 odd 嘅中文係咩咧？唔好意思，呢個我真係唔係好知個中文點樣翻譯係咩。好似都冇中文。勝算比或者賠率咯，有啲叫勝算比、勝敗比嘅賠，因為可以叫勝算比咯。如果你係叫做，如果台灣好似台灣咁翻譯嘅叫勝算比，即係咁呢度就係賠率咯，odd 就係賠率咯，咁 odd ratio 就勝算比咯。嗯。OK，客氣客氣，好，週末快樂啦。So any more question? This is odd ratio, but against will be 501, and odd is different from odd ratio. Is it okay? So I stay around to answer any question you might have. So any question? Yan Yan, Hui. Any question? No, we don't have quiz. No. Once we finish, I'll announce the quiz with a quiz next class. So don't worry. Don't worry about that. No quiz. Is that okay, Yan Yan? No. Will be assignment will be given next week because airdrop period is over. After airdrop period over, we give the assignment. So far there's nothing. Okay. Any more question? If I just stay. If you know, then you can feel free to leave. Do you have any question? And if I can help you? If I wait one more minute. If you don't have any question, then I will close the section. Okay. Then if there's no more question, then let me end the section.